you're going to get a lot of noise. You know, there's a lot of other charged particles, high energy, zipping through the Earth, some coming from outer space. Cosmic rays, high energy charged particles just travelling through space, coming through the atmosphere. The good news is they only get so far through rocks. Muons, when these cosmic rays hit the atmospheric particles, little muons which are very similar to electrons, they only live a few few nanoseconds at a very short half-life, they decay. But you don't want those things striking the nuclei of the experiments either. So for that reason, detectors are built deep underground, up to 2 kilometres underground. And you look 2 kilometres that way, imagine that underground, that's a long, long way, directly below the surface. And they're huge to try and get the numbers of nuclei there, you know, as potential targets for the neutrinos. So in the 1960s, this was the first experiment that was set up, a home state experiment by a guy called Ray Davis. It was 1 out of 4 solar neutrino scientists to get Nobel Prizes. It was that important to science. They got this big cylinder here, 380,000 litres of tetrachloride. That's essentially dry cleaning fluid. Why that? Because you've got full chlorine per compound, so you've got a lot of chlorine there. Chlorine's got a nice, relatively decent sized nucleus. And of course, if a neutrino were to strike that and change a proton into a neutron, you're going to get an isotope of argon. What do we know about argon? Argon is inert. You can drain it off very readily. It's not going to react any further. So they filled it all up there with this tetrachlorine and waited and waited and waited to see if the weak nuclear force was signs of neutrons going to protons, i.e. chlorine turning to argon. The hit rate worked out about 1 every 2 weeks. That big tank, 1 collision every 2 weeks, they've got a positive signal. That's what you wait on. 25 years later, 2 hits per month, they detected them. That was a huge thing. Neutrinos, up till now, was all theory. They said, yes, neutrinos do exist. We've detected them. Our theory's right. But we got a problem. There's only 1/3 the expected neutrinos we really would expect. If we got our math right, in terms of the temperature and to explain how hot the sun is and how big it is, it should be 3 times the number that we got. That became known as the solar neutrino problem. And it was one of 3 things. Either it was an experimental error, something was wrong with the instruments, maybe the standard solar model was wrong, or perhaps our understanding of neutrinos was wrong. So further experiments followed. This is the Cameo Candy experiment in Japan, where this time they filled this big tank, a couple of kilometres underground, 4.5 million litres of purified water. These big sort of PMT, photon multiplier tubes, like essentially photons, single photons of light detectors and amplifiers. They just put thousands of them around this big tank, filled it up with pure water. They waited for a neutrino to come through that tank, just by chance strike an electron, which caused the electron to recoil faster than the speed of light. We're talking high energy. And when something travels off faster than the speed of light, it gives off a certain type of radiation called Cherenkov radiation. You might say, how can things go faster than the speed of light? Einstein only said nothing can travel faster than the speed of light in a vacuum. In other mediums, such as water, there's plenty of particles that will travel faster than the speed of light. They typically give off that greenish, sort of bluish glow that you see on movies and nuclear power plants and stuff, when the villains are about to take over the nuclear power plant. You see the water glowing in blue or green. That's Cherenkov radiation. So they got the same number, slightly different technique. They said, look, we're only got the same problem, only the third the number. They knew it wasn't an experimental error. Then they were slowly learning more about neutrinos, and said, actually, there's 3 different types, what they call flavours of neutrinos. There's the electron neutrino, which is gets produced in the sun. But the electron's as an electron, and it's got sort of 2 family members called muons and taus. They're also little tiny particles. These guys aren't very stable. They decay very quickly when they form. They decay very, very quickly, so that's why you don't hear much said about them. But these guys have also got neutrinos to themselves. So was it something to do with this, perhaps? Then the theory says that these neutrinos don't have any mass. They travel at the speed of light, therefore they wouldn't have time to change later. Can't be that. Can't be. Let's move on. So then along came, they got the Kamikando experiment in Japan, and put it on steroids essentially, pumped it right up. They called it the Super K experiment. They did the similar experiment much on a much bigger scale. They were also able to identify the muon neutrinos, and they found that the flux or the amount of neutrinos, the daytime and the nighttime, from these muon neutrinos coming through the atmosphere was actually different. The daytime flux was greater than the nighttime flux. So that immediately was a clue that maybe these things are changing their flavours or types while they're travelling through the Earth. So it was suggested that muon neutrinos did transform. They didn't have the technology to detect the tau neutrinos. So we're getting closer to it. But if they do transform, which it looked like that experiment they did, clearly, if something's got time to isolate between a different flavour, it means it's got time. It's not travelling faster than the speed of light. When you travel at the speed of light, your clock is stopped. It's instant. You don't experience time. A photon can go right across the universe. It doesn't understand the concept of time because time stands still at the speed of light. But if something does something, like changes to another flavour, it's clearly travelling slower than the speed of light. That automatically means it's got mass. And up till now, the standard particle model of physics said neutrinos have no mass. So immediately they found, we've got problems here. We haven't understood neutrinos properly. And then along came the Sudbury neutrino experiment. They got this huge, spectacular size of the tank compared with a person. This is all 2 kilometres underground. They used heavy water, which has got deuterium in place with hydrogen for their water. They were using that, they were able to detect all 3 solar neutrino flavours, and they found the total flux exactly matched that standard solar model. That instantly proved that yes, the math's right, quantum tunnelling happens for real, classical physics happens for real, nuclear fusion is fueling the sun. Everything that they knew is correct. And also while they're there, they said, by the way, you guys in the physics department up there, your particle physics department, you better change your books while you're there too. We've just found out for you that neutrinos do have some mass. So that was huge. These guys won a Nobel Prize as well, from Super K and the K, all those directors, all those 4 experiments, all the directors got Nobel Prizes. It was that crucial to science and that important.
How long ago was that?
The Sudbury was, I think they started gathering data in 1999 and went through to about 05, something like that, 05. And the first one was Ray Davis in the late 60s.
He was in the Kings,
Sorry, he was
in the Kings.
Oh, the Kings was too, actually. So when he wasn't counting neutrinos, he was winding his guitar. So tonight we've shown you the standard solar model. It's nuclear fusion, the core of the sun, it's the source of its energy. Solar neutrinos, they're exclusive byproducts of nuclear fusion. Rather elusive, I should have said there, very elusive. There's trillions passing through Earth every second. They don't interact, they just see us as just empty space. But on the very, very rare occasion, they will collide with the nucleus of an atom, and if you can successfully detect them and quantify them, you're confirming a heck of a lot of physics theory and quantum theory. So when you get up tomorrow, appreciate the light and the heat from the sun. Just think of, enjoy all those photons as you're soaking them up. They're 1 million years old. And just think all those zillions and trillions of neutrinos going right through you as if you're just nothing. Every second, they're just zooming right through you. Have a moment's thought for them. So I hope you've enjoyed the chat, the initial chat of solving the solar neutrino problem. If you want a copy of the PDF file, just put us an email saying, hey, can you send me a copy? That's all good. And you're welcome to grab a card or write the number down if you want to get to play the movie. The movie is Alex Filipinko. He's a great lecturer, and he's going to give a 30-minute chat about solar neutrinos, which you already have the background. That's the whole point of this talk, was to set you up so you can go forward and enjoy it, know most of it, and actually then he'll expand on a few more details from there. So we're all good. Yep. And I realise that, time-wise, if someone wants to catch a bus or a train or a helicopter or a rocket, just that's fine. I won't be here. If you've got to go, that's cool. So I'll put the movie on.